Hi, it is section 4.4, the stochastic gradient method. The method was introduced by Robbins and Moeller in 1951. In the modern machine learning society, the method is one of the most widely used methods for large-scale optimization and one of the major methods behind the current AI revolution. The method was considered earlier in section 3.3 as a variant of gradient descent method for Adler classification. Here we'll study it in details for more general optimization problems. The method is also called stochastic gradient descent method, and we are using SGD for abbreviation. Now, that can be used to solve optimization problems in which the objective function is in this form, expectation of Fi. When I is taken from a finite number of values, then here the object function can be written in this form. It is quite common in machine learning. So summation and one of them, so in a sense, average the objective function from finite sum. Okay. The SGM is using the partial gradient of f of I, gradient fi, and rather than here gradient f. So partial gradient will be used as an approximation of the full gradient. That's the key idea of the method. Here we can write down the full stochastic gradient method. Input is initial guess, x0, and step size sequence. For each iteration, we are choosing I from 1 to m, uniformly at random. And rather than full gradient, we are using this gradient of one component and negation and scaled by now gamma n is added to all the iterates and now to get the new one. So that's the stochastic gradient method. And this stochastic gradient method can be much more efficient than the full gradient descent method. Particularly when the objective function consists of a large sum, because in each iteration we compute only partial gradient rather than full gradient, so it can be much more efficient. Here let's see this example, least squares problem, and that is 1 over m ax minus b squared, norm squared. It can be written as this form here. AR is the ith row of A. So once you try to minimize this objective function iteratively, then you may use the stochastic gradient descent method. Now, the choice of step size for the stochastic gradient descent method is quite delicate issue. For the method, the backtracking line search is not an option because the line search would involve to evaluate the object function at each iteration a few times. So with that, the efficiency of the SGD will be destroyed. So the line search is not an option, which means that you have to choose step size earlier. There are two popular step size strategies for the method. One is constant step size, and the other one is decreasing step size. Constant step size is quite simple. For every iteration, you're using a constant gamma, and the method, once you use this strategy, then the resulting method converges very fast in the beginning, but around the local minima, and the iterations are bouncing around. So it is not recommended. And for decreasing step size, here the method guaranteed to converge when you are choosing gamma n and satisfying this equation. The summation of gamma n is infinity, but summation of gamma n squared is finite. For example, here gamma n is a constant over n, then summation of that term is infinity. However, the summation of the square of this term is bounded. And with this decreasing step size sequence, the method around the local minima, and it is not really bouncing, but because it is decreasing, so also you have to be careful that the convergence slow down, and then it may not reach the local minima. Okay, let's see example. Here, that is along with constant the step size. The gamma is 0.2, and that is now stochastic gradient descent. There are only now two directions, two components. So two components are x direction, y direction, randomly chosen, and the iteration is going on here. And it goes very fast in the beginning, but later on, the iterations are bouncing around the minimum. Now, that one is now decreasing the step size. Here, in the beginning, reasonably going, but later on, slow down, so that for this, the poorly conditioned function, and because now the step size becomes smaller and smaller, so that eventually here it is stuck around here and cannot reach to the local minimum. However, and the stochastic gradient descent method is converging for a wide range of problems with a wide range of choice for the step sizes. So it is working quite nicely in most cases. Now here, the method is using only the one component, just so that the gradient estimation is quite rough. It's not really accurate. However, it is convergent. What is the reason for that? The answer for the question is due to the unbiasedness property. Okay, let's see here. Unbiasedness of the SGD update. Let En denote the expectation with respect to the choice of random sample I at iteration n, and here, because the index I is chosen uniformly at random, but a distribution must be uniform, so that for each I, the probability of the being accessed is the same. So if there are m components, then each one has probability 1 over m. We have this equation, expectation of gradient fr is same as, now that can be computed, expectation can be computed by using here the probability, and so that here we can get this term. But if we assume here the probability is 1 over m, because the uniformly at random, then this term can be written in this way, so that eventually this is the same as the full gradient. So expectation of the gradient of one component is the same as the full gradient. This is the crucial property that makes the SGD work. And you can see the full proof from the reference 7. Okay, that is the end of the section. Thank you.